Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. We are in module 11, we are still continuing with X-ray diffraction, and in the lecture 5 we will be covering again intensity of diffracted beam, some other factors of how they influence the intensities. Until up to now we have discussed about mainly one factor which determines the intensity, that is structure factor, and we have derived an expression of structure factor from by taking right from an how X-ray scattering happens from an individual electron, and then how that sums up for an atom, and then all the atoms which are part of an unit cell. So, from there we have derived an expression of structure factor, and then we have derived the structure factor for various type of crystal structures like simple, base centered, body centered, phase centered, and more complex one like sodium chloride. We did that in the last class. And now we will be moving forward, and we will be trying to talk about some other effects which are responsible for modifying the intensity of X-ray diffraction beam. So, one of them is multiplicity factor and temperature factor. This is what we will try to cover here. Absorption factor possibly we will discuss in the next lecture. So, the first one is multiplicity factor. So, what does multiplicity factor do? So, multiplicity factor is basically responsible, or it is related to the multiplicity of various crystallographic planes in a crystalline material. So, for example, if we take the simple cubic system, just a simple cubic system, the unit cell is shown here. So, in this simple cubic, if we consider something like 100 type plane. So, I believe everyone knows about the type of planes and a specific plane, the difference between a type of planes and specific planes, whereas the curly brackets, basically HKL in a curly bracket means the type of planes, like combination of many planes which are possible with a permutation combination of this number, especially for cubic system I am talking about, or I am not talking about other complex systems. And when there is a first bracket, instead of a curly bracket there is a straight bracket like this, that means a specific plane. So, it is basically the multiplicity of any type of plane or class of plane, the multiplicity number, how many permutation combination you can make, that also affects the intensity of the diffracted beam. The question is how? So, we take a simple example. We take something like 100 type plane of a simple cubic structure. So, 100 type planes means this side plane. So, there are 6 such side planes possible from this cube, this simple cubic unit cell. There are 6 such side planes possible. And since it is a cubic system, all of this, everything A, B, C, all lattice parameters are the same and angles are 90 degree. What happens is that if I consider this family of planes, this 6 side planes, and 6 side planes means I can consider them as either 100 and bar 100 basically, and then 010 and 001. This 3 types, basically this means these 3 sides, sets of sides, these 2 planes, these 2 planes and these 2 planes. If I consider like this, then what I will see is that they will be basically having the same d value, the distance between, because everything is same here. So, the distance between these 2 planes, these 2 planes and these 2 planes is exactly the same. Interplanar spacing is basically the same. So, they will be satisfying the Bragg's condition exactly at the same 2 theta position. If I take now the X-ray diffraction profile here from the simple cubic structure, I will see that I will get only one peak corresponding to this 100 planes, 100 type of planes or 100 family of planes. I will get one single peak out of them because they will be satisfying, they are having exactly same d value. So, if lambda remains constant, d remains constant, then sin 2 theta will also be constant. That means, they will be forming a diffracted beam exactly at the same angle, meaning all the diffracted beams coming out from all three sets of planes, they will be sort of coinciding with each other. So, ultimately I will be getting a peak which is a combination of all 6 planes. The beam, diffracted beam coming out of all these 6 planes will coincide. I can imagine that they will be summed up and they will be forming this one single peak belonging to 100 type family of planes. That is fine. Okay. Now, if I consider instead of 100, I consider something like 111 plane. So, 111 plane can have, if I just have to write it, if I write, then it will possibly be even more clear. If I consider something like 111 plane, family of planes, and this here I can write, this will be having something like 111, this will have 1 bar 1, and then I can have 1 bar 1 bar 1 and 1 bar 1 1. This 4 type of planes, again this means these planes and their opposite, just putting a bar on top of that. So, opposite. So, these 2 sets of 111 planes similarly will be forming again, their d spacing is exactly the same, it is a simple cubic structure. So, their d spacing is exactly the same and they will be again forming the peak in the same position, same 2 theta value. Now, the point is that in a 100 type plane, I can make this combination, I can have 6 such planes, 6 side planes, whereas in 111 type plane, I can have 8 such planes. So, 4 here and reverse opposite 4 opposite planes. So, there are 8 such planes possible in case of 111 type family of planes, whereas there are 6 such possible planes in case of 100 type of plane. That means, the relative proportion of 111 type plane is higher than 100 type plane. So, if I consider that each of these planes are giving some amount of intensity, the way we calculated it for, if you remember the structure factor and the way we calculated the intensity from one single atom. So, if I just imagine that, then that means 8 111 type of planes are giving me an intensity versus 6 100 type planes giving me an intensity. So, ideally the 111 type plane should have a higher intensity. If I just imagine that all the atoms are giving the same intensity of the diffracted beam, scattered beam, then the 111 planes should have a higher intensity compared to 100 planes theoretically. It is not happening here, not shown here because of other factors, but ideally that is what it should do. Now, this is called, so how do I take care of this multiplicity or the number of planes possible in a family of plane? So, that factor is known as the multiplicity factor, and the way we can define it, it is basically, let me bring that laser pointer again. Okay. So, it is the relative proportion of planes that is contributing to the same reflection. Okay. So, relative proportion 100 type of planes, all of them contributing to the same reflection, same place, they are giving the satisfying the diffraction condition and for the same 2 theta value. So, this number, the relative proportion, that is known as multiplicity factor, and that goes in the final intensity of the scattered beam. So, it should be multiplied with its multiplicity factor. Okay. And it is the way it is defined is basically the number of different planes possible in that family of planes with having the same spacing and structure factor. That means, the number of permutations, basically the number of planes or number of permutations possible for the position and sign of this plus minus h, plus minus k, plus minus l in a h scale plane. So, again if I write it down or already it is there, I think already 111 is there. You can just imagine that 111 and bar 1 bar 1 bar 1. So, 1 1 bar 1 bar 1 bar 1 1. So, like this 1, so here this plane opposite to it will be bar 1 1 1 and opposite to this will be 1 bar 1 1 bar 1. So, this 8 planes, so that is the number, that is the multiplicity factor. And In this case, of course, the multiplicity, when we calculate the multiplicity factor, remember one thing, that parallel planes with different Miller indices. So, these two are parallel planes. If we consider these two as two parallel planes and these two, if I consider them something like 100 type of plane, I have to take 100 and bar 100. One of them will be 100 plane, one of them will be bar 100, and it is very relative because you can shift the origin here. So, these two should be taken as two different planes. So, ultimately the multiplicity factor for 100 type of plane, 100 family of planes will be 6 for cubic crystal, at least will be 6, and for 111 type plane for the cubic crystal it will be 8. So, that is the multiplicity factor. Ultimately the intensity I get for 111 plane should be multiplied with 8, whereas the intensity, final intensity I get from 100 plane should be multiplied with 6. That is a multiplicity factor that goes here. Okay. Now, the important point is that multiplicity factor basically depends on the crystal structure, what kind of a crystal structure, and why is it so? That is basically if we consider a tetragonal crystal. So, in a cubic crystal we have seen the multiplicity of 100 family of plane is 6. What happens for a tetragonal unit cell is that in tetragonal we know this A and B is same, but C is not equal to A or B. So, C axis is a different, it is of different length. So, what happens is this planes, these two, this top one and bottom one, this planes, the interplanar spacing will be different from 4 side planes, these 4. So, this plane and this back plane and front plane, this will have the same interplanar spacing which is equal to A, whereas this planes, the top and bottom plane will have an interplanar spacing of C which is not equals to A. So, that means in case of a tetragonal crystal, 100 and 001 planes, they do not have same spacing. So, I should consider them separately, and the multiplicity factor for 100 planes, the 4 side planes, the 100 planes will be 4, whereas the multiplicity for 001 plane which is different than 100 plane will be 2. So, here I have to consider this is a different case from simple cubic, here I have to consider them separately, and if you look at this diffraction pattern here, if you see the diffraction pattern here, then you will see that we are getting 220 and 0202. So, basically both of them are from 220 family of planes. They are counted as two separate planes here. If you can see here, the 220 for a simple cubic system, 220 type of plane is only one. There is no difference between 220 and 202. These are not two different planes. These are same family of plane for a cubic system, but for a tetragonal system 220 and 202 are two separate planes and they appear separately in the X-ray diffraction pattern. That is why when we calculate the intensity of these two, we have to take them two separate. Here 220 planes we can calculate their in multiplicity only once. Here the multiplicity of 220 and 202 planes will be completely different. So, that is the effect of multiplicity factor for various different crystal systems, and that makes the intensity calculation even more difficult, because till now we are considering only cubic system which is very symmetric, tetragonal more symmetric, much more like compared to cubic less symmetric, but compared to other crystal system it is much more symmetric. If you go to orthorhombic system, it becomes even more complicated. For example, orthogonal system, all 110 type planes are different. So, even cubic system 110, there are only two types of 110 planes. Okay. So, 220 and 202 type. In case of orthorhombic crystal, all 110 planes are different, and that is why they will be having multiplicity factor of 2. So, any plane, unique plane will have multiplicity factor of 2, because that plane and the reverse of it. So, 110 planes for orthorhombic crystal, all of them are different and all of them will have different crystal or different multiplicity factor, and that is what is shown here, that if you consider body centered cubic versus body centered tetragonal versus body centered orthorhombic systems, then 100 plane itself, for cubic system 100 type of planes are all same, all 6 are same, whereas for tetragonal system again you have completely different type of 101 and 110 planes, and then if you go to orthorhombic, you have all 3 different type of all 100 planes, they are different, completely different. If you go to 200, again here in case of cubic system, all of this family of planes are unique, means all of them are the same. All the planes are same, the multiplicity factor is one unique value. They will give you only one single peak, whereas if you go to tetragonal, if you go to orthorhombic, you will be getting different peaks for them with different multiplicity factors. So, if you see this orthorhombic crystal structure here for iron selenide, then you will see 110, 011, 101, all of them for cubic, all of them is 110 type family of plane, but for an orthorhombic system, you are getting them completely separately 110, 011, 101, all of them are giving separate crystalline peak because they are separate planes there. Obviously, their multiplicity factor is also different in this case. All of the multiplicity factor for each of them is 2 in this case. So, that is the effect of multiplicity factor in determining the intensity, absolute intensity of various planes. Okay. So, the next factor that we need to consider is called the temperature factor. Now, temperature factor, what is the effect? As the name suggests, it is something to do with the temperature itself. Fine. So, when we calculate the intensity, basically when we just simply calculate the, let us say, structure factor, when we started with an electron intensity of an scattered X-ray from an electron, then we went to the atom, then we went to the unit cell. One thing we sort of assume that this intensity calculation, we did not consider crystal, or rather we consider crystal as a collection of atoms which are located at fixed points in the lattice. That means they have no movement, no vibration. So, this is what the condition possibly we have assumed, that at any given point of time all of them are situated at a fixed distance from each other. There is no movement, they are just touching along certain direction, they are touching and they are fixed, they are rigid bodies which are fixed in their position. But we know that atoms undergo thermal vibration about their mean position. So, there is a vibration, and that we discussed about that during phonon scattering and all. So, atoms move about their mean position even at an absolute zero temperature. Absolute zero temperature, it is very minute, but still it is there. So, even if you increase the temperature, of course, this amplitude of this movement, this motion, this thermal vibration, the amplitude of this increases as the temperature increases. And if we think that it is something at a higher temperature at any given point of time, this, because of thermal vibration, the distance between these atoms are continuously changing. It is not a fixed one. Continuously there is a movement and the distance between the atoms are continuously changing. Now, the amount of this thermal vibration is not something you can neglect so easily. For example, if you take aluminum at room temperature, the average displacement about its, for an atom, about its mean position is around 0.17 angstrom, which is almost 6% of the equilibrium distance between the atoms, closest approach of the mean atomic position. Basically, that is the equilibrium distance. If you remember, or if you have saw this, that this, what we are talking about is this. One second. Basically, what we are talking about is this equilibrium distance of separation, where force, if you can write the force, this is the equilibrium distance. Okay. So, this curve, interatomic potential versus, or this is interatomic potential, I am sorry, this is not force, this is interatomic potential. So, interatomic potential versus distance curve. So, this is the mean position, and this distance is almost 6%. The thermal at room temperature, the atomic vibration is almost 6% of this this equilibrium distance here. That much of thermal vibration, that much of change in the atomic position can happen just by increasing the temperature all the way from absolute 0 to room temperature 273 Kelvin. Okay. So, now this increased or this thermal vibration, this amount, this is almost similar, this amount that we are seeing here, this 0.17 angstrom. This distance is almost the distance of separation between electrons within the atom itself. So, that means if I assume that entire atom is vibrating and this much of distance is there, they are covering, that will impact the intensity of the diffracted beam, because this, in this situation, what we can just now understand, in this situation, the constructive interference that is basically finally forming the diffracted beam, and that is what is separating the diffracted beam from a scattered beam, regular scattered beam. The diffracted beam is special phenomena where constructive interference is involved. There will be a certain problem, or there will not be a complete constructive interference just because of this movement, this atomic movement, which is of the order that is enough to modify, or that is enough to affect this entire phenomena of constructive interference. Okay. So, this thermal vibration, let us see how this thermal vibration can affect the intensity of the diffracted beam. The first thing it can do, does this thermal vibration, is it can expand the unit cell. So, if we imagine that this is one of the atomic planes we are seeing here, we can imagine that due to thermal vibration, now the atoms are sort of further apart from each other, and the unit cell has expanded. That means, if the unit cell is expanded, that means we are getting now a change in the lattice spacing, we are getting a change in the interplanar spacing. And if we have a change in the interplanar spacing from the relation, again lambda equals 2d sin theta, we are having a change in the d value. Obviously, lambda is a constant for any incident X-ray, d value is changing, we will be getting diffraction at a different sin theta value. So, we will not be getting diffraction condition satisfied at exact Bragg's condition, we will be getting it in different, other than non-Bragg angle, other angles there will be a diffraction condition satisfied, just because the unit cell is now expanded, and that means this d value is changed. So, this is first effect that this thermal vibration can cause. Now, if we can measure this peak width somehow, if we can measure this position of diffraction, this diffraction lines, how much shift it is showing in terms of 2 theta, in sin 2 theta, how much this shift is happening due to the increase in temperature, that means due to the change in d value, due to thermal vibration the change in d value, and how much 2 theta, how much change in sin 2 theta is happening, if we somehow with temperature, if we somehow measure it, that can help us to identify the thermal expansion coefficient of the specimen. Just from an X-ray diffraction technique, we can find out the thermal expansion coefficient of the specimen by measuring the two peak positions with respect to the temperature. That is possible, and that measurement is very accurate if the X-ray diffraction has no other issues involved with it. The issues that we will be discussing maybe in the next module, if those issues can be solved in such a way, this is one very nice method to find out the thermal expansion coefficient of any material from X-ray diffraction, but I am not going into details of that. Fine. So, that is the first effect, that shift in the 2 theta position, the peak will be shifted in the 2 theta position. Okay. Even more prominent effect that this temperature, the thermal vibration will produce, is basically the intensity of the diffraction, intensity of the peak will decrease, whereas the intensity of the background will increase. Background in the diffraction, the entire other scattering angle, the background, that intensity will increase. The peak intensity will decrease and the background intensity will increase if we increase the temperature. Now, why this is happening, that is what we have to understand. Okay. What we said is that due to the temperature, of course, now this atoms, we go back to this geometric construction for Bragg's law determination, we go back there for base centered, body centered, we know. What now we are imagining, that when we were seeing this entire construction, we were imagining that all the atoms are fixed in their own position. That is why we were considering for base centered 100 planes, we were able to consider all of the atoms lying on the same plane. And for this base centered, body centered consideration, we were able to imagine a extra plane in the middle. Now, what is happening here is, because of the thermal vibration, all the atoms may not lie on the same plane. Okay. So, this atoms may be lying, this atom perhaps possibly lying a little below than this one is possibly a little above than this, because of this thermal vibration around this position. Same thing for these atoms, all of this. Now, what will this make, or what the effect this will have, is that this entire constructive interference, the constructive interference needs, the path difference has to be an equal integral multiple of the wavelength. So, this entire geometric condition, but because of this thermal movement, because all of these atoms are now having little movement in their atomic position, so this distance will be also changing. Let us imagine that this distance is basically changing due to that increase in the temperature. So, I am increasing the temperature and this distance between these two atoms, these two atomic planes are changing. So, that means the constructive interference, this path difference will not be an exact integral multiple of the wavelength of the incoming X-ray, and that is why we will not be getting an exact constructive interference from parallel set of planes, or in other words, the reinforcement of this waves that is scattered at exact Bragg angle from parallel planes, this will not be as perfect as it is for a crystal with fixed atom. When we imagine that this d value is changing, basically the reinforcement will not be that perfect from parallel set of planes. Okay. So, and obviously that will affect the final intensity, because only in the event of constructive interference, extreme constructive interference, we will be getting highest intensity. If anything less than this constructive interference, if any partial interference happens, then the intensity will automatically decrease. Okay. So, now if we imagine that this thermal vibration, due to this thermal vibration, the average displacement of atoms from its mean position is something like n u, then this reinforcement of this rays from two different parallel planes, this reinforcement will become more imperfect as the ratio u by d decreases, or as the ratio u by d increases. That means, if this displacement around their mean position, if this increases with respect to the d, the atomic position, then this imperfection will also, the reinforcement will be less and less perfect. That means, we will be moving away from a perfect constructive interference. Of course, what it means is that the intensity, as I said, the highest intensity is obtained when there is a perfect constructive interference. Now, we are moving away from the perfect constructive interference case. So, as the temperature increases, that means the ratio u by d, temperature increases means u increases, even if d is constant, temperature increases means u is increasing, and that means now the intensity of the, we are going to more and more imperfect situation, the intensity of the diffracted beam will also decrease. That means, if temperature increases, intensity of diffracted beam also decreases, even if we get the same d value. I am considering, so earlier we were just considering the effect of d is still there. The effect of increasing d is reflected in the shift of the peak in sin 2 theta axis, the peak will shift. But now we are considering the movement itself, the vibration, the average displacement it has about its mean position. Because of that, temperature is increasing, u is increasing, d remains constant, we are getting we are moving away from an exact constructive interference case, the intensity is decreasing. That is the first effect. Okay. The second effect that it can have is basically same thing. If we are reinforcement will be becoming more and more imperfect, okay, or less perfect if this ratio u by d increases. Now, even if the same temperature, at a constant temperature, same temperature, let us imagine that u is constant. As theta increases, that means as we are moving towards higher and higher diffraction angle, sin 2 theta, we are moving from something like a forward diffraction to backward diffraction. So, if the sin 2 theta is increasing, theta increasing, then this d value will decrease, that because height 2 theta involves. So, the reflections, the diffraction for low d values will increase, will be more at higher 2 theta. So, this comes basically from the same relation, lambda equals 2d sin theta. So, d and sin theta is inversely proportional. For lower d value planes which are much closer, or high index planes, basically high index planes which are much closer to each other, for them the diffraction occurs at a much higher 2 theta value. So, those planes, for them this ratio again u by d will automatically increases. So, even at a constant temperature, u by d increases for higher 2 theta. So, as the theta value increases, the diffraction angle is increasing, again we are getting higher u by d, but this time because of the d increases and we are getting d decreases, we are getting an increase in u by d as theta increases. That also will be affecting the intensity. So, even at a constant temperature, thermal vibration will cause a greater decrease in the intensity of the peak at high 2 theta values than at a low 2 theta values. So, this both the things. So, increase in temperature itself will decrease the intensity because U will increase, and that decrease in intensity will be more prominent at higher 2 theta values. Those peaks which are giving for those low index planes or high index planes which are having low d value, for them this decrease in intensity due to increase in temperature will be much more prominent. So, ultimately all those effects are combined into one parameter which is called the temperature factor and expressed as E by minus E raised to the power minus 2m. I am not going how it is derived and all, which is a number that is by which the calculated intensity is to be multiplied, so that we can finally get the diffracted intensity with temperature correction. And this E by 2m, as we just now discussed, that it decreases as 2 theta increases. So, highest is basically at 0 where it is 1, that means the intensity, the temperature effect is lowest at there, and anywhere we go at a higher 2 theta value, basically going higher 2 theta values means the way it is impacting is sin theta by lambda. This we have already discussed in atomic scattering factor. So, I am not going here. So, basically sin theta by lambda, if we sin theta by lambda increases, this factor basically decreases from 1. So, it becomes a fraction. So, if we multiply the diffracted intensity with something like this and compared to versus something like this, obviously the intensity will also decrease. The intensity will be lower when we are going to higher 2 theta values. So, that is the relationship, or that is what the temperature factor all about. So, more about the temperature factor we will be discussing in the next class, and also we will be discussing about the absorption factor in the next class. Bye.